So those are examples of property charts. Now let us see how the material index example that we visited during lecture 2 gets implemented in the context of material index. Let's take, for instance, a square cross-section beam, and you basically, across two supports, you apply a load F, and that results in a deflection delta. The cross-section width is B, and so the cross-sectional area would be B square. Let's say the mass of the beam is M. The length of the span over here is L. Rho is the density. So then the stiffness of the material is the ratio of F over delta. And for this beam, the deflection delta is basically dependent upon the load, the cross-sectional span, L cubed, a constant which depends upon the loading considerations and the cross-sectional geometry. Here that constant is 48. Depends upon the modulus, and also depends upon the second moment of inertia, which again is a geometry factor. In this case, a square over 12. Suppose for this particular function, the constraints are such that L is given, and it is required that the stiffness exceed a certain minimum amount, S star. So, as we looked at over here, if you look at inserting the value of delta into this equation and substitute for C, you will get this term over here for stiffness. If the objective is to minimize the mass of this beam, right? Mass is area times the length, and so you get a volume term over here. If you multiply that by the density, you get a mass term. So if you now solve for A in this term by rearranging this, you will be able to get the performance metric in this case, right? It's a combination of the stiffness criterion, the geometry, and this material index of rho divided by e to the power 0.5. Conversely, you can take a reciprocal of that because E was plotted against rho. You can derive that from those plots. And so you end up choosing materials with the largest E raised to half divided by rho. There's a reason for choosing a maximizing function as opposed to minimizing function, as in the case of minimizing mass over here. And we will visit that during module 2. So, how do we use these material indices with the CES EduPack? That's part of the module 2, but largely for a light stuff B. If you end up taking this material index, squaring both sides, and rearranging the terms, right, you will have E to be rho square times m square. If you take log on both sides, then log E will be 2 times log rho plus 2 times log m, where capital M is the materials index. So you see the significance of this factor 2 in this plot of log E versus log rho. That means the slope of a line in this case will allow us to be able to either eliminate options for a light stiff beam or select options. And if you keep increasing capital M, the material index, you will be able to choose materials that comply with that constraint. Depending upon the overall geometry, whether it's a tie rod, whether it's a beam, or whether it's a panel, the slope ends up changing. And just like we have done the derivation for the beam, it will be useful to be able to check how to be able to derive that for the tie rod as well as the panel. So this chart can be used for designing light strong structures of various cross-sectional geometries. While currently the EduPack version that we will be using in this class primarily takes simple geometries and connect them to material selection tools. Recently, ANSYS has bought the whole CES EduPack product offering and are incorporating it into their overall geometrical design, CAD design software. And so it will be possible to apply the same kinds of constraints and material selection rules along with the ANSYS package. So basically you have a situation where materials offering the greatest strength to weight ratio lie towards the upper left corner. Some things to look at. In the strength versus density plot that we looked at over here, the version of strength that is considered is different for different materials. For metals and polymers, it's the yield strength. For ceramics and glasses, it's the modulus of rupture. So the testing method is different. For elastomers, it's a tensile tear strength, and for composites, it's a tensile failure. So for metals and polymers, the yield strength is plotted and estimated at 0.2% elongation for metals and 1% elongation for polymers, because intrinsically the two materials offer very different elongation levels. For brittle ceramics, the modulus of rupture is plotted. Typically, the modulus of rupture is greater than the tensile strength, but very much less than the compression strength. For ceramics, the compression strength is about 10 to 5 times larger than the modulus. For composites, the tensile failure strength is plotted because you have fiber buckling that occurs that affects the overall strength of the properties.